Swayam Prabha. Digital India. Educated India.
Hello students, I welcome you all to this lecture series on quantum chemistry and spectroscopy. In this course, we will go through this interesting world of quantum mechanics and we would see the relevance of quantum mechanics in chemistry. But before we do that, we would in today's class discuss why was there a necessity for quantum mechanics, how the field of quantum mechanics originated, what are the reasons behind it, what are the stories behind it. That will be the broad topic of today's lecture. By the end of 19th century, physics had made significant progress and there was a feeling that the field was stagnating after seeing a rapid progress in many different subfields of physics. For example, by then the classical mechanics was well understood thanks to the seminal work of Newton, Hamilton, Lagrange. Elasticity, hydrodynamics were well understood. Thermodynamics, the concept of entropy, heat engines were all popular by then. Electric effect, magnetic effect were all well understood. Even statistical mechanics, thanks to the works of Boltzmann, were also very popular and were well understood. At the same time, chemistry was also witnessing rapid progress. By then, the periodic table was more or less settled. Kekule had his famous dream about the benzene structure and chemical kinetics had progressed quite a bit. At this juncture, there originated two subfields of physics that changed the face of science that we know now. There were, one is theory of relativity, the other is quantum theory. Theory of relativity dealt with systems or the bodies that travel at very high speed to the limit of speed of light. On the other hand, quantum theory deals with subatomic particles, microscopic world. These two theories, the theory of relativity and quantum theory, together constitute what we call modern physics. These two fields introduced many new terminologies in the language of science. They brought forth many interesting ideas which were unheard of before. For example, theory of relativity talked about time dilation, space-time wrap. On the other hand, quantum theory talked about uncertainty, wave-particle duality and things like that. Together, these two fields revolutionized the fate of science. Although theory of relativity has had very little influence on chemistry except for the great relativistic effects in heavy elements. On the other hand, quantum theory had profound influence on chemistry. So much so that in today's world, quantum chemistry is an integral part of any chemistry department or any chemistry syllabus. Modern research in all fields of chemistry heavily depend on the progress of quantum chemistry. Today's organic chemistry, today's inorganic chemistry, biological chemistry, materials chemistry are strongly influenced by our knowledge of quantum chemistry. So, in this course, we will learn more about quantum chemistry, but before that, in today's class, we will discuss about the stories behind the birth of quantum mechanics. How did it come into play? It was not like that a smart person on one fine morning decided that okay, I should do something interesting or revolutionarily and then there was birth of quantum mechanics. No, it was not. The birth of quantum mechanics was a prolonged process. There were experiments after experiments which were pointing out the lacunae of classical mechanics or the classical physics that we had understood. The experiments were not we were not able to explain those experiments by our existing knowledge. And at that point of time, quantum mechanics came out as a savior to explain many interesting experimental effects. In today's class, we will discuss about some of those experiments that classical mechanics could not explain. Our first example is the black body radiation. We all know that when we heat a substance, it emits radiation. As we keep on heating it more, the color of the radiation keeps changing. There exists an ideal body that absorbs and emits all radiations, and this ideal body is called black body, and the radiation that it emits are called black body radiation. When one carries out experiments on this idealized body, the black bodies, one sees the spectral density that comes out as a function of frequency has some dependence like this, as it is shown here. As one can see, the spectral density which is plotted in the y axis, has strong dependence on the frequency of the emitted radiation. These spectral densities, different curves represent for different temperatures. So, that means, if the black body is at different temperature T1 or T2, T3 up to T6 different temperatures, then how the spectral density evolves or how the spectral density appears for different frequencies. If we look at any particular plot here, suppose we consider T4, then we see that the spectral density is maximum at a particular frequency over here, and at both lower frequency and at higher frequency this spectral density decreases. The maximum of the spectral density we can see keeps increasing to keeps going towards higher frequency as we increase the temperature. Now, the area under this curve, the spectral density versus frequency curve, represent the energy per unit volume of the black body. So, as you can see that the area under this T6 curve is significantly higher than the area under this T1 curve, for example. This makes sense because the black body at higher temperature T6 can emit more energy than it can do at a lower temperature T1. The existing knowledge that came out from classical physics gave us some idea about how spectral density could depend on frequency. Existing knowledge from classical physics suggested that the spectral density rho would have a dependence on frequency as nu square. If I plot this rho as a function of nu square, this would appear something like this. This curve, this line simply goes up as a function of nu square, the frequency square. Now, what you observe here is that at lower frequency, the agreement between the classical mechanics prediction, which goes by the name Rayleigh Jeans law. This is the prediction by classical mechanics, also known as in this case Rayleigh Jeans law, and these are the experimental curves. As you can see, at lower frequency, the agreement between the predicted curve and the experimentally observed curves, the agreement is good. However, at higher frequency region, the agreement is measurable. In particular, in the ultraviolet frequency region, UV region, this agreement is extremely bad. So, this problem was popularly known as ultraviolet catastrophe. Why was this called catastrophe? The reason is the following. As I said that the area under these curves represent the energy that the black body is emitting. So, if you try to find out the area under the curve that the Rayleigh Jeans law provides, you would see that since this curve is unbound, it simply goes up as a function of frequency nu. So, therefore, the area under this curve is in principle infinite, because this is not a bounded curve. Now, since the area under this curve is infinite, that means Rayleigh Jeans law predicts that any black body at any temperature would emit infinite amount of energy, and that is not what we are observing, and that is also not a meaningful result to have. So, this ultraviolet catastrophe was bothering the scientist at that moment, and that is when Max Planck looked at this problem. When Max Planck looked at this problem, he observed one thing, that at the higher frequency radiations appear only at higher temperature. For example, you see this, the spectral density of the frequencies in this region is present only in the T6 curve, whereas these frequencies are not present in T1 or T2 curves, for example. So, one observation is that higher frequency radiations come out only at higher temperature. By then we knew that higher temperature meant higher energy. So, at higher temperature the system or the oscillators that constitute the black body, they had higher energy, for example. But we did not know how energy is related to frequency at that time. So, Max Planck's first observation was that he saw that since higher frequency arise, higher frequencies are activated only at higher temperature. So, he suggested that perhaps there exists a relation between frequency and energy. The energy in this case is the energy of the oscillators that absorb or emit the black body radiations. So, what Max Planck suggested is that the energy of these black body oscillators is proportional to nu, the frequency, and he carried out several experiments to find this proportionality constant, and it turned out the proportionality constant he gave the name of h, which is the famous Planck's constant. Which has a value of 6.626 into 10 to the power minus 34 joule second. This is his first assumption that he made. Second, he said that not only energy has a dependence of frequency, but also the oscillators of the black body oscillators can absorb and emit energy in integral multiples of this h nu. So, what he suggested that the energy of these oscillators are h nu multiplied by some integer n, where he suggested n is an integer 1, 2, 3 and so on and so forth. Once he made these two assumptions, that energy is proportional to the frequency and the black body oscillators absorb and emit radiation as integral multiple of h nu, and then he did some simple exercise which actually reproduced all the experimental curves beautifully. So, Max Planck's idea, these two assumption could resolve the problem that we are experiencing in black body radiation, and we understood that what could be the physics behind it. However, at that time these two assumptions were quite revolutionary. For example, in particular, when one tells that the energy of the oscillator is not continuous, that means the oscillator's energy the oscillators cannot have any energy, rather they can have only some discrete values of energies like 1 h nu or 2 h nu or 3 h nu or 4 h nu. This discrete nature of energy or the quantized nature of energy was very perplexing, because so far we always thought that we human beings, we invented numbers. We invented numbers to make our life easier, to count things. We thought that nature perhaps did not know about this number, but here is an example where we see that the experimental observation can only be explained when one assumes that the energy of the oscillators is not continuous, rather is a discrete and quantized, it can take discrete and quantized value. This is how Max Planck could resolve the black body radiation problem, and now we will look at another example. How classical mechanics could not explain the experimental observations. The next example is the photoelectric effect. We know that when we shine light on a metal surface, beyond a point, when we provide enough energy to this metal, the metal will lose an electron, and this electron is called photoelectron, and this effect is photoelectric effect. And this electron that comes out of the metal, we can observe it by connecting it through an electric circuit and looking at the current. The photoelectric effect had a simple premise. It said that the kinetic energy of the electron EKE is simply energy of the light minus phi 0, or the work function of the metal. Each metal has a given value of phi 0, or the work function, which is the threshold amount of energy that you must supply before the metal can leave out its electron. So, the energy that you provide to the system must be greater than your phi 0, and the remaining part of the energy, after taking care of this phi 0 or the threshold energy, the remaining part of the energy is translated to the kinetic energy of the electron. So, that means the ejected electron that comes out of the metal would travel that much faster if you provide higher and higher energy. At that time, classical mechanics had a wrong notion. It suggested that the energy of light actually corresponds to its intensity. That means, what it wanted to explain, when one wanted to explain the photoelectric effects through the knowledge of quantum existing classical mechanics, it would have meant to the following effect, that if I use high intensity light, that because intensity corresponds to the energy in that sense. If I use high intensity light, I would be able to do observe photoelectric effect, and by increasing the intensity of the light further, I would see that the kinetic energy of the ejected photoelectrons are increasing. However, the experiments told a different story. The experiments that were done were suggesting that at some particular frequencies, even extremely low intensity light could eject photoelectron, and we could see photoelectric effects beautifully even with very low intensity light. But on the other hand, some other color light or light with some other frequency, even when we are using extremely high intensity, they were unable to show photoelectric effect. So, what was going on there? This problem was resolved by Einstein. His essential assumption was that the energy of this light E is not proportional to the intensity, rather it is proportional to the frequency of the light. And the proportionality constant, he carried out several experiments and experimentally determined the proportionality constant as h, which had exactly the same value as we had in the black body radiation effect, 6.62 into 10 to the power minus 34 joule second. Now, this is a completely unrelated experiment to that of black body radiation. However, the experimental result suggested that the energy is proportional to frequency with a proportionality constant of h as the same value that we got in the previous. So, in this case, the energy of the electromagnetic radiation or energy of light is E equals h nu. Then Einstein had another assumption to make. The second assumption is that the energy of light comes in some packets, and these packets Einstein suggested a name for it, and it is used, they are called photons. The energy of this light come in certain packets, and the energy of this packet is given by h nu. One packet of energy corresponds to the h nu energy of one packet of light energy corresponds to the value of h nu, where nu is the frequency of that light. When you change the wavelength of the light or the frequency of the light, the energy of that packet of that light of that photon changes. And the third assumption, which is kind of related to the second one, is actually that the light, which we always knew as a wave, has a particle like nature. Light has particle like nature. Now, with these three assumptions, Einstein could explain the photoelectric effect. We will go through the arguments now. For example, since we have the energy now proportional to the frequency, it could easily explain the experimental observation that some light which have higher frequency, they could emit photoelectron even at lower intensity. Remember, when we say that intensity is proportional to energy, in that case what we mean is that we have to have high intense light to do to show the photoelectric effect. But now we are telling intensity is not related to the energy of the light, rather frequency is related to the energy of the light. So, therefore, if your frequency matches or frequency is beyond the threshold energy phi 0 or the work function of the metal, then the photoelectric effect should be observable. And if the frequency of the light is lower, the energy corresponding to the frequency of the light, if it is lower than the work function of the metal, no matter how intense light you bring, it is not going to show you photoelectron. The photoelectric effect will be absent. That is because the energy is related to the frequency and not intensity. Now, what does intensity mean? Intensity in this in the new explanation represent that how many packets of energy are there in this source radiation. For example, high intensity light would mean that you have many photons of the same energy corresponding to the frequency. So, now the frequency meant energy and the intensity meant how many packets of energy are there in that radiation source. So, with this explanation, the anomalies that were apparent in photoelectric effect experiments could be easily resolved. Here one must point out that we discussed so far two different experiments, one the black body radiation, another the photoelectric effect. They are completely unrelated experiments. However, it turned out that in both the experiments we suggested that there is some quantization. In the photoelectric effect, the quantization was the energy of the oscillators, and in the in the black body effect experiment, the quantization was for the black body oscillators, and in the photoelectric effect, the quantization is the in the sense of energy of the radiation. And in both the experiments, we had this proportionality constant of a relation between energy and frequency with a proportionality constant of h, which is the Planck's constant, and both of them have the same value. So, there is something deeper and more fundamental that was not understood by then. So, it was by looking at these two completely unrelated experiment, it was apparent. Now, in this lecture, we discuss this effect, and in next lecture we would actually go through some more experiments and see how many more experiments could not be explained through existing knowledge in quantum in classical mechanics, and how new ideas fundamentally different from what we knew before, how new ideas were coming forward and how new ideas were needed to explain those experimental results that we are seeing. This is where we would conclude today, and then we will continue in the next class. Thank you.